world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe.
All right, hello and welcome to Celestial Theodolite update number 39. So we just had a debate on the Celestial Theodolite. I assume there's going to be a lot of questions, comments, etc. So we'll get into all those here in a second. But before we get into that, I wanted to talk about the geometric intersections of mountain peaks and the refraction situation, right? So it's been as we were just talking about earlier before we went live, the computational models for the atmosphere assume a certain amount of air density to make the computations uh, fit into the modeling. And for that, like that's the driving factor of it. That's how you can input real world data into it and then get the same values when you go to calculate astronomical refraction. It's based off of that core air density model or value. So because the data is now, or because the data was presented as like, oh, this is how much refraction there has to be because it was confirmed from a weather balloon. Well, let's go and recap the refraction intersections for mountain peaks, since that's the exact amount of value. Like I've been saying for, even before this debate, the stars should be lingering if there's a refraction to the degree in which they say there is, in the same way that when the sun sets, it lingers above the visible horizon. The same situation should happen with the stars. So when the stars set, they should be above the peak. Now, to start us off with Pike's Peak here, they're sticking to 13 arc minutes of refraction. So that's again going to be almost 2 arc minutes over the peak, which corresponds to 10 seconds. When we look at the occlusions here, let's see. What's the celestial bounty? Just a quick example of the occlusion. What never happens is the star lingering in the mountain peak or anything like that, or lingering above it or sliding along it. Now, it was said to explain a conjunction in the 1800s that uh, between Saturn and Jupiter, I think it was, or Saturn and the moon, something like that, that Saturn was refracted up by 4 degrees and it just slid along this mountain peak. But no one's ever seen anything like that. No one sees stars behaving like that. They occlude when they, as soon as it hits the mountain. And for the stars that are of a larger angular size than like the normal ones, we've seen from the videos that they basically set into it. They occlude within seconds. Like they get smaller each second because they're literally getting blocked. They don't linger above it or anything like that. So 2 arc minutes above the peak physically. And then more importantly, when you get into the, let's see, just those pictures. 1 second here. Central angle analysis. 1 second. There we go. When we get into these refraction values, remember, the null hypothesis is falsified by geometric intersections. Okay. When comparing what the globe physically predicts, not saying, hey, this is what is an apparent, this is the apparent yada yada. What geometrically should occur, they add the exact amount of refraction back in and cut it off to make it match the timing difference for flat Earth. Because on a globe, as per chord tangent theorem, you don't see over this curvature line here, and the sky is already tilted to your horizon. So the star only has to drop half of the arc length to intersect with the mountain peak. Never occurs. It always occurs when the star traverses the full arc length. That should never happen on a globe. Like when we showed the time of occlusion being in favor of the globe, it would make the flat Earth off by the amount of curvature that we didn't predict for. No, it's never what happens. So we go into Blodgett Peak now. Blodgett Peak is almost 3 arc minutes above the peak. If you want to do the apparent position, because some people like to say, well, if we increase the elevation of the peak by the apparent position by terrestrial refraction, then it'll geometrically intersect with the apparent position and cause the occlusion, even though no one that I'm aware of yet has produced a mirage and then shown a light source being occluded by the mirage. That would be an interesting one, because most people don't like the refracted image in the glass and all that. They say it's not analogous. Just make a mirage and then have a light source go behind the mirage and see if it gets blocked by the mirage. But anyway, if you add the mirage, it's still going to be over by 1 arc minute and 23 arc seconds, which comes out to 7 seconds. So it would still be above it, not even intersected with it. Let's see. So Cheyenne. For Cheyenne, they would be 2 arc minutes above the peak. For the terrestrial refracted one, they would be closer. They would be within 30 arc seconds. That's pretty close. That's 3 real world seconds. And then for the physical intersection, though, they're off by 15 real world seconds. Pretty significant. Neither of those occurred. The occlusion happened when the star's true position intersected with the mountain peak at the end of the arc length. Blue Mountain. Hmm. 2 minutes above, which translates to 17 seconds.
Or even the app is closing down on them.
1 second, Ken, your mic hotting. I'm gonna mute you for a second. For the apparent intersection or whatever, that would be 3. But again, show me the mirage, and then we'll talk about this as a possibility. All right, Mount Rosa. 2 minutes of being above the peak there, so 14 real seconds. And again, so adding 15 arc minutes of refraction to the amount of terrestrial drop, again, giving the apparent globe. Like it's been argued that, you got to use the apparent angle. Well, that's an apparent globe, not a geometric globe, and that can't possibly falsify the null hypothesis. Green Mountain, 4 arc minutes above the peak. Comes out to 30 seconds in difference. They add back 19 arc minutes of refraction. They need to hit 15 to be what the globe would actually geometrically predict to hit their timing. So what they would have to do is cut this short by the 4 arc minutes and just say, oh, well, there happened to be 4 arc minutes less this time, even though if there was no mountain peak, they would be happy to tell you that this is the amount of refraction. And they know because they measured the atmosphere. So, yep. Let's continue on here. Oh, let's look at the geometric. So for the geometric here, they'd still be above by 2 arc minutes. There's no consistency in the apparent model. That's why the geometric intersection judgment is the baseline. It's like there can't always be the exact amount of refraction to compensate for the curvature every time. And then sometimes even more. So let's see, where are we at? We're at green green, go to North Peak. Now, North Peak is an interesting one because here we would be 3 arc minutes above the geometric peak for the globe. But if you add in terrestrial refraction over that distance, the star would be below the refracted peak. But that's not what was observed. Right. So this whole idea of like, we're going to use the apparent as, and stack it, that's not it's not a real thing. That's no consistency to it. So the occlusion would have happened 30 seconds earlier when it intersected at this that wasn't observed. Let's see here. We got getaway. We got getaway. Now, in particular, in regarding the astronomic refraction values, Kat and I actually went to this location at 6 months apart, and the temperature difference was about, I think, like 20 degrees off the top of my head, somewhere in there. And that temperature difference didn't matter at all. It changed it by like less than an arc minute, if I remember. So, like I said, there's a specific model that allows you to input the real world values to get the exact amount of refractivity that there needs to be, and the refractivity is driven by the air density. So, all right, let's see here. We got getaway peak. Yeah, let's getaway. Houndstooth. So here was a shorter distance at a higher elevation angle. The globe predicted to be, let's see, positive would be below the peak at that time. So they predicted that they would be below the peak at the time that the star emerged. And actually, I think I need to change the sign. Yeah. Yep. I think I need to change. Hounds is positive then. Well, anyway. Let's see. Parent positive. 37. Right on it. Oh, that is the apparent. Yep. Okay. So yeah, still below it. And then for the refracted position of the peak, that's basically the same because there's almost no terrestrial refraction at that distance there and angle, so comes out to be basically the same amount. Got Old Blinn. Now Old Blinn is an interesting one because here the apparent position would have already been 2 arc minutes over the peak. So it would have already emerged at that time by 13 seconds earlier. And then for the refracted intersection and what have you, it would have emerged 7 seconds earlier. Didn't happen. You see that the air difference split between us is over the amount of arc length that was lingered. And when that gets divided up, because the globe is always off by what they predict as curvature, they end up being off by like 3 times as much, and then we end up being off by the difference of that. Like that's what creates these differences. So if we subtract 82 from 121, we get 38. That is the drop over distance, and that's how they remember the errors are split between us through this theorem here about the proportionality between the drop over distance of the arc length that we're analyzing. We're analyzing this distance here is the arc length, so that's why we share this share that same drop over distance amount. So when we convert it into meters, we can see what these total up to. So what the globe missed their geometric intersection by ends up being the the difference there, like as a residual. So, all right, then we have a further distance at Blinn. Here the star would have emerged it was basically almost 3 arc minutes above the peak, 2 arc minutes and 40 arc seconds. So it would have emerged 17 seconds earlier. Never happens. Same with the apparent position of the peak would have been 7 seconds earlier. And again, the refraction amount the globe predicts, what's it called? 11 arc minutes of refraction. I'm sorry, 11 arc minutes of drop. Then you go to 25 arc minutes of refraction, adding it, so that's like double the drop over distance there. Why you would go? Why would you? Why you? Why you would try to prove a geometric globe by going to a position where there was the most refraction? It's crazy. But you can see that these differences are closer to flat Earth for the intersection differences again, because it's relative to the arc length in this gamma relationship. As soon as this midpoint gets traversed, it becomes less and less globe, and then there's only one thing at the end of this arc length, and it's a mountain, and it either has a rise over run to it in elevation, or rise minus globe drop over run. And if it's rise minus globe drop, then that star is also going to be following that relative to the observer, and it would have already intersected. All right, so we got
That's a really good diagram.
Thanks. And we got S.E. Varley here. Now we've been told, oh well, isn't this number what the globe predicts as drop over distance, and when you derive the elevation? Well, like I've been saying, the relative part of this is this intersection difference, excuse me, because that's relative to the original arc length. The original arc length in this case for S.E. Varley is 16,600 meters, which comes out to be an angle of 9 arc minutes. That's 59.9 arc seconds. I'm just going to call that a niner. So half of that, 4.25, is going to be the drop over distance of that. Now remember, as a globe lad, you're standing on a sphere, so you're already deviated on the horizon. That star following said curvature of Earth already deviated with you. So that's why you only perceive half of that. So as it's continuing that arc length, it only has to traverse 4 arc minutes of it before it gets occluded. And it ended up not only traverse, and then so we see this intersection difference here at the time of occlusion is 9 arc minutes, the full arc length. So how did that happen? And we're only off by 4 arc minutes. So how did this happen? Well, the star lingered beyond the time at which it would have intersected, and it lingered 30 seconds longer, which corresponds to 4 arc minutes of motion, almost 5 arc minutes. So instead of traversing 9 arc minutes, it traversed 14. We predict the full arc length, so we're only off by 4. The globe predicts half of the arc length, so now they're off by double because of the lingering. So that's the relationship between what these values represent and the air differences between them. Because remember, we're assuming the linear rate for the stars with respect to sidereal time for the idealized conception. If there's deviations from that, this is what the deviations would look like in the measurements, and how the air differences would be split between them. So these are residual airs, all of them, from the intersections, from the stars lingering, essentially. That's what I think. Because on a flat Earth, they're not going to go beneath your feet at a certain point. They're going to, stop descending and just kind of be moving away from you. So, all right. Now this is the place that Kat and I returned to from getaway during December here. And also Brian was with us. Shout out to Brian and his sister and brother-in-law. And so we got these measurements with a different temperature value there for the refraction, changed it by less than an arc minute, and we got the same, same results. Intersection differences are in favor of us. The apparent intersection here For the peak, though, for the refracted position in the globe is only 23 arc seconds, though. That's pretty close on the apparent position. So if you want to add double the arc length back as drop, almost double the arc length back as drop, as refraction, and say that, you know, to match us, that's I'll allow it just this one time. All right, and then we got lucky peak here. So this is a really interesting one because the stars emerged here. This is an emergence over a short distance at a 6-degree angle here. Globe predicts like the drop over distance between us isn't very much. It's only 2 meters here, but the stars end up emerging before their refracted positions, you know, even come close to the peak. Here their refracted positions off by 3 arc minutes. 3 arc minutes to the apparent peak if you want to add the 13 arc seconds of refraction. But yeah, ended up missing it by just a little bit. But again, this one's pretty much, you know, one of those scenarios where they're kind of indistinguishable. But again, here, what we're looking at is the alignment with the true position over the arc length rather than the apparent. All right, and then let's see. So we went over these graphs and stuff a week before the debate, but just to quickly show these again, the relationship between Earth curvature and the correction. Hope that's the full gamma. 1 second, we need the half-Cs. So the relationship between these here, adding it exactly back in for an apparent globe in every scenario. So now I myself have not had the time to go through the stuff that Astronomy Live presented yet. I know Shane's dabbled in it a little bit. Shane, did you want to present what you're finding so far or talk about what you noticed in it?
Yeah. Did you want to comment on the nature of the debate first before we do that in any way or anything?
Yeah, I was dissatisfied with the presenting new things without showing what they were first, or you know, without you know, that was so doesn't matter, dude. It's fine.
Yeah, we'll go through what I found.
All right, you want to live stream?
Let's see.
All right,
Yep.
if you can join Shane's live stream here. Yeah.
We're good. I'll give
Yep.
everyone a second. So we went to his GitHub for a little bit, and I downloaded some of his CSV files here. Now he's got quite a few. I guess his general premise was he replicated our method by getting his data from this ray tracing program and using weather balloons, right? So in his data table over here, he has our observations, the star name, and you know all the relevant data on the right here, the time, all the stuff that we usually had, lat long, observer position, elevation, observer, all that good stuff. But all over here, it's got a weather balloon data file. So each one of these peaks is attached to this CSV file. Those files look something like this. I don't know what most of this means. This is just his equivalent data. This is the result of his program that led to his data, and this is his results table. That's what we're going to look at. So there's a wonderful, cool method to do our method differently, but somehow he's going to arrive at almost all the same results. So looking at some of the data here, of course, lat long, time, all of this is legit. Star name from a different catalog, no big deal. Everything in color here, I think I changed the title. Everything in bold I added, so I added these for sure. Because everything is in decimal degrees, right? So that's fine, but I can't really read decimal degrees, so I added a degrees, minutes, and seconds conversion for each one of these. And all this does, of course, is the standard divided by 3600, divided by 30, divided by just to get this decimal degrees column into a readable, for me, arc minutes equivalent. So I did that for most of these. He's got the geometric position here. And all of this sort of checks out. He's got his flat Earth prediction. The only thing that doesn't check out is his actual comparison at the end here. Is he's not comparing flat Earth prediction arctan rise over run to star position from mountain. He's comparing flat Earth for flat Earth. He's comparing arctan rise over run to geometric position of star from mountain. But for globe, he's comparing terrestrially refracted globe to a celestially refracted geometric position. So he's not comparing globe to globe. He's comparing globe to these two. He's taking his actual position over here, so the geometric position, 232, minus the star refraction. So we're going to subtract the 13.5 degrees for our curvature, and we're going to compare that to our prediction, and we're going to be fine. And then that equals out to his error margin over here of 0.01 degrees. And if we look at what he got for his globe error, it's over here, 0.1001. So again, all of his output is just CSV. So this is all Python data output from a computer program. There is no actual formulas or comparisons or things that I can find in here. It's really just a Python export. So all of the formulas in here are just from me inputting this conversion. So it's hard for me to see what he actually did. But if I can replicate this exact result precisely, then I'm pretty sure this is what he did. And his globe degree error column matches my column if he compares globe geometric to position minus celestial refraction, and then put that in the same comparison to flat Earth to geometric position. So again, that's an apples to oranges comparison. However, if you use all of his data and you put it in the same sort of aggregate comparison that we do, and here's just a pivot table, which means I didn't manipulate any of his data. I'm just aggregating it differently, or I'm showing it in different parameters. And all I've done is show, the actual true position for all of these observations compared to the flat Earth prediction and the globe prediction. Actually, let's use this one. True position. So the actual observation, this is the actual angle of the star at the time of observation. This is the flat Earth prediction for that observation, and the globe Earth prediction for that observation. Now, his globe Earth prediction, instead of being geometric solely, is actually geometric with terrestrial. So he incorporated terrestrial refraction right into his geometric, and it was too difficult for me to separate and pull it back out. So we'll just use his globe terrestrially refracted, because that's what he has in his data. To him, globe geometry is synonymous with terrestrially refracted globe for some reason. So that's his data. And again, here's the true data. Now these two are just comparison columns. This just says how close is this to this, and this says how close is this to this, right? So these are added, but they are only comparison of these two. This is all his data converted into degrees, minutes, seconds, and arc minutes over here. So if you do the same geometric comparison as the cell Theo, so literally if you take his data and do our generic comparison the Dr. Mike came out with 39 weeks ago, turns out that you get all the same results. So if you look at Pikes Peak, if you look at the globe prediction 219, Ruhif would agree with that. Flat Earth prediction 230, actual 232. We're off by 2 arc minutes. He's off by, globe's off by 14 arc minutes. That's all of these are closer to flat Earth. So these are all Pikes Peak observations with different stars, and these are close enough to our results that I think that this is our method. So he used ray tracing from super awesome weather balloons to fill out his data table to get information that was almost exactly the same as our end result, except he used a completely different comparison point to make it seem as if, this globe is method. And again, we're using an apparent celestially refracted globe compared to a geometric, in principle only, flat Earth, right? So this is data here.
And the name of that third tab down there is quite inflammatory. I just thought I would point that out.
I have no comment on that. There's when we're looking at actually the airplanes that he added, doing his ray tracing to airplanes, if I didn't touch any of his data, again, for the airplanes, and I can't confirm this is what it's going to end up when we go through the Python code and see what his actual program did with his ray tracing to output to get the data that we have here. But if you just compare true position that he had in his table to the flat Earth prediction of rise over run and arctan rise over run to the globe Earth equivalent prediction, turns out that these 4 planes are also closer to flat Earth. So you got Allegiant 453, supposed to be at 7 degrees 53 arc minutes. We're at 15 arc minutes off. Globe's 32 arc minutes off. American Airlines 1517, we're 18 arc minutes off. They're 39 arc minutes off. And then there's jet speed over here. They're 22 arc minutes off. We're 8 minutes off. So all I think we're going to be incorporating these planes as data points into our site moving forward, just because they're awesome. And thank you for adding to our data, and thank you for your participation, sir. But if you look at the actual data that he said debunked the whole thing, he got all of the same data that, if you correctly compare it, produces all the same results that we stand on all the time. And as it turns out, actually the only globe position is to avoid geometric comparisons at all costs and do everything you can to make it about a twice refracted globe. And this data shows unequivocally that he had to do so. He double dipped refraction. The observation has terrestrial refraction built in, and the geometric comparison is to a completely different point. He's not comparing it to what he's comparing it to flat Earth. He's comparing it to an already celestially refracted globe. And that's pretty much all I had to say about that.
Nice.
Thank you, sir.
So he took the same position as our buddy John.
Successfully sleuthed.
Yep.
How long did it take you to do that, you said?
Like 20 minutes. I did it at work, and you asked me when you were like, "Did you look at it yet?" I was like, "No, did you?" Shit. Hold on.
Nice. All right. We will now take open questions and stuff. So if anyone has any questions, comments, or concerns,
You can always count on me, but maybe someone else wants to go first.
I'll go first. It's just a single comment, actually. Alan, when I'm looking through everything that you're displaying on your spreadsheets, it's all very complete. It's all very detailed. It has many different categories and a lot of data slicing, very, very, very hyper analyzed. But looking at all of the figures, again, not so intuitive for the crowd. I am left wanting for a graph.
Ooh.
Like, I'd really like to see a graph, because you got 20 data points. I'd like to see something between distance to peak on one axis and pick your type of refraction or compensation on the other axis. I'd love to see that kind of data.
I'll trade you one graph for one peak. Or how's that sound? I'll give you one graph. So if you tune into my stream, you'll see this awesome Desmos thing that Brian just made that shows the elevation differences between the two. And it's two scale here. So let me back this up a bit. So it has the elevation profile of Pike's Peak from the center of the mountain to all the way to Mike's house. And then the elevation difference on a plane versus a globe. And we have the
altitude cross section. Gotcha.
Yeah, you like that? That looks very Manistone in my opinion. Very high quality there.
I don't know about that, but it's good info.
I've never seen Manistone use Desmos one time, to be honest. I don't know.
Yeah, not once, bro.
But yeah, they end up being off by the curvature over the arc length, and they would need, the refraction to bend it back down. Well, they would need the refraction to bend it over and then bend it back down. But in any case, that's step one of what you asked for, Stone, possibly? Nope. Okay. All right. I take your silence
we could talk more some other time about that.
All right. Well, when you do your measurement,
Your graphs are
I
unsatisfactory.
expect the sickest graph ever graphed to man. So.
Oh, dude, you should see my pre-production on the measurement.
This dude's pre-producing it. I love it.
I don't know why that diagram you had up for the full arc length traversal versus the half arc length. For the first time seeing that, I understand what you meant the whole time when you kept saying that, and I never really understood it until just today. Dude. But I'm looking at it like, oh, that's what you mean by half. That's what you mean by full. Well, I mean that's the good representation of why the globe only gets half, because of the curve. Because you don't see past the middle of that section right there because of the curve. That's crazy.
Yep. It's that's called chord tangent theorem. Proposition 32nd. The proportionality between the deviate or
So I
between
guess
the tangent and the chord is proportional to the inscribed angle of the arc length.
so. The only argument I've heard from our Globers, our Globe leaders here, and from your opponent of Astronomy Live on Friday, was that the Globe doesn't care about geometric intersections, meaning they don't care about the physical Earth curve, which you'd have to say leaves them arguing from a geometrically flat globe, which appears curved, right? Wouldn't you say, like, so if you don't care about physical intersections, you don't care about geometric intersections, you want to use apparent and refracted transitions and occlusions, then you live on a geometrically flat, optically curved globe, bud. No?
We have a picture here from like on that point. We have a picture here from Pikes Peak from Mike's house or thereabouts. And if you zoom in here, this is where like there's obviously some cars here, but this is where the horizon is. This is where that midpoint would be. This is where the 200 meters of mountain elevation difference is being hidden behind this midpoint here. This is, the globe lads might say that, the horizon's apparent, right? But somewhere in here, the apparent horizon and the geoidal horizon intersect. Well, we should be able to test that in some meaningful way. And it turns out we can't because apparently the exact amount of refraction to change the results to match flat Earth is exactly the amount of drop over distance in this elevation difference between the mountain and Mike. Like so, like the geometrically
Yeah.
want it to explain the horizon observations, the difference between the apparent horizon. But when it comes to geometric comparisons for celestial phenomenon, it's like, no, can't do that. Can't do that.
Or they're comfortable with it never being there. As long as I can mathematically correct it back in, I'm good with that. Like, I can live on a globe that's only there in calculations, I guess. That's what most of the globe seems to be saying to me. That's what most of our globe friends seem to be saying.
Indubitably.
Hey,
All
Alan,
right.
can you hear me?
Yep. Give me one sec. So there were.
All right, Alan, Jesse's just spoken up. He's asking you a question.
I heard him. I was about to say next week or whatever because I was busy with the debate stuff and had a little sinus infection. Uh, so I've been kind of not on as much. But I got Ruhif's thing to go over next week, and John did a presentation, so we'll be going over John's Prezi or whatever, and then I think that's what we got lined up for the upcoming stuff. But what was your question, Jesse? What's up?
Well, and I'm not asking you to do it now, but I think it would be really helpful if you could go over the steps of why I think that the occlusion timings we get are expected on a globe. You know what I mean? Why refraction should be taken into account
Whether or not it should be taken into
on a globe.
account or not, it's the exact amount to compensate for curvature of said globe. So I'm not super interested in that because the end result is the same. So if there's no way to falsify or establish geometric intersection predictions for the globe, then the globe is apparent based on flat Earth geometry. You can add as much refraction corrections in as you want.
There's no geometric way to make that happen.
So are you saying you're unwilling to go over
Flat
what I
can't
have?
be.
I mean, if you're unwilling, it's okay. I'm just asking.
Correct.
I think you actually would agree with every single one of my foundational claims.
I already do,
Well, no.
and incorporating them just recovers the flat Earth angle, so it doesn't change anything whether or not it's there or not. So you're arguing an apparent globe with based off of flat Earth geometry.
Well,
That's what
if
happens when your prediction is
light curving was part of reality, then wouldn't it make sense to recognize that the light may be curving and not just falsely assume that it was always straight?
It's the same amount every time. Regarding geometric intersections, you specifically went to a place that had the most refraction to not get that for some reason. Like if you're not down for geometric intersections to try and geometrically prove the globe, you have a different goal, my friend.
physical Earth curve, Jesse. You're correcting the
The
physical Earth curve with two types of
the only
refraction. That's why we don't agree.
the only model that could take a geometric similitude as the globe is the concave Earth model. Only a sphere within a sphere or the inversion thereof in some other stuff can match the same. Flat can't do that.
Well,
Flat can't equal a globe.
it's actually
Flat can't. There is no way to. Okay, go ahead,
actually,
Al.
yeah, the globe is actually flat Earth minus globe drop. So they're intertwined in that relationship as per chord tangent theorem. And secondly, the atmospheric model, like I said, is dependent upon air density assumptions to make uh, the refractivity plausible. And the amount of air density was derived from empirical observation of watching circumpolar stars at different elevation angles and taking the difference of where they should be versus where they're at or visually. So it's not based off of like measurements in the lab or anything like that. And they have computational models to run them through so that you can take real world values, put them in, and it'll give you, the exact amount of angle that you need to get for a correction based off of quote unquote real world atmospheric conditions. It's a computational model. It doesn't have to necessarily have anything to do with reality. So saying like I don't know what you were trying to equate or talk about, but this is, you know,
Man,
Are you saying that we're
that
seeing the
that
real position of the
it's so
stars
hard to respond to because there was.
3% or 3
Hold on,
degrees
hold on, hold
above?
on, hold on, please. Sorry, Wesley. Sorry, Wesley. You're next. You're next. You're next.
Yeah.
That's so hard to respond to because you said so much. But my idea is simple: is a sphere or a globe or whatever you want to call it, in a flat version, there is no equivalent version. Distances or the proportion of whatever you have on this sphere, you know, distances. If you have a ball and you have a string and you put, needle to needle and you have a string from point to point on a ball, and the actual length of the string from one point to one point means something, real proportional distance. You could take this globe and flatten it out into any, there's so many ways. Any of these ways at one point or another on this ball, it takes those string lengths and changes them. So in one version, the string length on the globe in Antarctica, which is, from this point in Antarctica on the ball and this point in Antarctica, it's not that long. But if you were to take that to the Gleason and those string length changes because that string is now around the whole world. And so in one view, the length of the string means something. It represents a proportion. It
yeah,
represents a scale where this idea works anywhere
yeah.
on the world.
I think I see what you're saying. Can I hop in for a second?
If you take this proportion, if yeah, if you get it, then yes, thank you.
Cool. Great, great. Cool. So in the coordinate system that we're using here, right, the string in this case is a meter. A meter is a ratio of the coordinate system itself, and the coordinate system is defined by how long you have to traverse in distance before the star changes into 1 degree. And they use a ratio of that. So if you use a ratio of that, it's always going to be internally consistent. And an AE map is just a projection of the same coordinate system. The distances aren't actually different lengths. It just optically looks that way because it's projected out in concentric rings and flattened. So it makes them bigger. So if you use an AE map and you try to plot a distance and whatever, based off of the distance of your string, you have to apply a specific correction to it so that it plots correctly. So the size of the string will appear bigger, but it actually represents the same distance that it does in either hemisphere. So that's kind of a misconception that you have and kind of not really related to the celestial theodolite in terms of geometric occlusions. Because what is mutually exclusive isn't the ratio of distance traveled to star moving, because you could technically make that anything. The Chinese used the celestial sphere. They were geocentric flat earthers. They used a unit of measurement called a li. The quote to quote mainstream narrative, the actual definition of a li has been lost to time. So we're all the scholars have now just agreed that it's half of a half of a meter. So now that they've made it half of a meter, it's always, whatever they calculated would have been half off of the actual dimensions. But obviously, if the Chinese were using a li in their own system, if they calculated something to be 1500 leagues away, it would be 1500 leagues away, because it's internally consistent that way. It's only now looking at it through the lens of trying to make the meter physical and stuff, that that they bind it to that, but it's always a ratio of the coordinate system itself, so none of that really matters. But what would be mutually exclusive is geometric alignments for occlusions based on geometry. So that's kind of what we're talking about. So slightly separate from the from what you were talking about, though.
Um, that was a good amount. I mean, I appreciate it. I
No
don't want
worries.
to I don't want to detract too far off the point. If you could remind me of what the overarching point is, so I don't.
Yep, gotcha. So the overarching point is we're using the celestial sphere model to test the terrestrial sphere model. The terrestrial sphere says that an observer standing on the sphere is going to be deviated by a specific amount, and it's actually a ratio here of the half central angle of whatever distance they're looking at the horizon. So, in any case, what this translates to, this difference between flat Earth and a globe, is this elevation difference, which equals a timing difference on occlusions for stars. So, when stars get occluded, they should get occluded earlier on a globe because the observer is already half tilted. Essentially, you can think of it that way. So the star only has to traverse half of the arc length to get occluded by the mountain peak, whereas on a flat Earth, it's not going to be dropping over any distance, so it has to traverse the full arc length, so it takes longer before it gets occluded. So we're testing for mutual exclusivity of elevations of mountains based on the intersections of stars.
I think Wesley was
I got you. Thank you.
Wesley. You're trying to get in
Thanks.
before.
Yeah, go ahead, you.
Oh, sorry. Go ahead, Wes.
Yes, please go ahead,
Yeah,
Wesley.
I was just asking. Yeah, if I see a star at 2 degrees above horizontal, is that the true position of the star, or is that a refracted position?
I don't think you ever see the true position. You always see some refracted position or some apparent position of it. You never see directly to the true.
So why can't so why can't Mountain Peak occlude the refracted position of the star, the refracted light from the star?
That's not my hypothesis. My hypothesis is that the elevation of refracted position is over the peak, so it's not under it yet. So if it's over it still, it can't be under it, right? So it can't be occluded if it's not under it. So if they say there's a specific amount, that
So
full amount has to be used.
so when you said that you think that the occlusion occurs when the star, the peak, and the observer are geometrically aligned, is that accurate or is that inaccurate to your position?
It's accurate to how you perceive it, but the alignment was due to the geometric, like the true position of it, like whatever the light source of it would be. That's what That's what actually intersected with the peak, and then it would optically occluded for you.
Okay, sorry. Let me just ask so I'm very clear on what you're saying. So, do you believe the occlusion occurs when the star, the mountain peak, and the observer are in a straight line?
Yep.
Okay. So, why why can't why can't the star be actually truly below the peak and being refracted down, so and then occlude then? That would not be accurate to the globe model.
It could be, but the thing is, in every scenario, it's always the exact amount to match the end of the arc length for the rise over run of the peak for the mountain, because there's only two possibilities for it to be there. So you can't say there's 13, almost 14 minutes of refraction and then cut off 3 of those minutes or 4 of those minutes to match the flat earth prediction. Like that's like at that point, that's that's just absurd.
Yeah, well, what I would say is it's absurd, and no globe earther would believe that the when those three are in geometric al- alignment, that that's when the occlusion happens. The star would have to be much slower than the peak in order for that to occur.
Well,
So
irrespective of what
that's
they
just a false
believe,
premise
yeah,
from it's a straw man. Okay, well then you're just denying that refraction exists from the star to the mountain.
I haven't denied that at all.
That's what it seems to me. Okay, well then why are you saying it has to be in geometric alignment? Because if it was refracted, it wouldn't be in geometric alignment at the time of occlusion.
Well, that's what the data shows. That when it traverses the end of that arc length, it occludes at a mountain that has a rise over run angle to it. That's why the intersections are always closer to what we predict.
Okay, I mean I just
Is
don't understand why
it
that would be your
it
first
it
your.
because it's the geometric implication of it. That's why we're interested in geometric intersections.
We don't,
And the fact
yeah, we
that
don't see geometric.
that's why we use timing
We don't see
intervals of
geometric.
occlusion. That's why we use timing intervals of occlusions to measure the difference.
Have you ever
That's why it's not
thought
based on
about doing
optics. That's
that?
why we deny using optic angles.
Hold on a second. Okay. Have you ever thought about doing the occlusion between the geometric position of the sun and the horizon and the observer?
Ooh, great question. I have been posed with that, but that doesn't lead to a mutually exclusive outcome because you could say that it's setting, geometrically plus the refraction. We could say that it's setting geometrically just because it's, moving away from us and it's an optical phenomenon. Oh, I'm sorry. We would say that it's moving away from us geometrically and it's an optical setting. There would be no way to have a mutually exclusive outcome in that. What we could use, though, is a mountain that is big enough in angular size. So when the sun gets occluded by it or sets into it, we could do something like that for sure. But just the observation of it setting alone wouldn't be helpful. That would be kind of the same as if like we went out to sea and we just observed the stars setting into the marine layer. Like, it would be could go either way, right? So that
No,
that
no, no.
mount
Setting
the
into
mount
the no,
yeah,
setting into the horizon.
there's a little opaque layer called the marine layer that's above the sea. That's the horizon that it
Not with
sets
the
into.
sun.
No,
Not the sun.
I said stars at
Not
the
the sun. Why don't you do it with the sun?
it would be the same with the sun. There's
Yeah,
no
why don't you do
difference.
it with the sun?
There's no mutual exclusive elevation difference.
Where's the marine? Where's the marine layer and the
Even
horizon?
even without the marine layer,
What?
there's still a layer that it sets into.
What's that layer called?
Couldn't tell you. The atmosphere? Like, come on, dude.
I can see the
What's the
ground, and
quickest
I
way
can
to
see
get to the solution?
So
half
here's the
of the
thing.
sun.
So here's the thing. Hold on. Here's why can't we do sun at the horizon? Here's exactly why. I'll tell you. Give me 1 second. Prezzies. Why it's in here. Okay. So just using the horizon alone, the globe lads will invoke up to 10 degrees of refraction to explain this phenomenon of the sun being already set 16 minutes ago, but still lingering in this layer of the horizon that you just laughed at because I don't know the name of it off the top of my head. So unlimited amounts of refraction will
No,
be
do one.
invoked.
Do one where
Yo, yo,
yeah.
listen,
Hey,
guy.
Alan, do one. Do one where we don't
Yo,
have that.
yo, listen, guy. Listen.
Of
Listen,
don't call me
it
guy.
it it's still, yeah, your guy, because it still doesn't lead to anything mutually exclusive. The mountain elevation is what
Why?
gives us the mutual exclusivity. It seems like when mutual exclusivity wants to get introduced, the globe lads want to go, hey, how about we do something that just reifies the globe? How about we use a
No, do
mountain
one
elevation?
where we can see the horizon, where we can see half the sun. Do one where you see half the sun cut off by the physical horizon, not where you have this cloud layer or whatever you want to call it. Do one where there's not that, where you can see the physical
Where
horizon,
there's
where you
no
can see half the
atmosphere,
sun.
bro. What are you even talking about?
No, no,
Number
no, I didn't say
one.
that.
And two,
I didn't say
listen,
that.
listen,
I didn't say
Wesley,
that. Listen to what
Wesley,
I'm
On a
saying.
clear day.
Wesley, if it doesn't lead to
Why
a
are you getting?
because if it doesn't lead to a mutually exclusive outcome, I don't care. You would say that it's setting behind physical Earth curve. I would say that it's optically setting at your limit of vision. There's no mutual exclusivity there. It doesn't lead to
Why don't you say
anything
that for the mountains? Why don't you say that for the mountains then?
because there's a physically different elevation difference between them. And you can't say that the elevation difference
Use
every
zero.
single time is made up by refraction compensating exactly perfectly for the curvature of Earth. That's
But the
preposterous.
elevation doesn't even matter. Like in
Use a
stellarium, it doesn't
zero.
matter. You could
Yeah,
put the
use
elevation
zero
to
elevation.
0, you're going to get the same answers if you put it way up.
We're talking
And
about
you're not measuring elevation anyway. You're just doing timings, right? It's all
Pinky,
about timing.
Pinky. We're talking about when there's specific alignments relative to the
Alan,
observer versus relative to the peak. Of course, the angles are going to be different, and elevation is determined that way through the timing at the occlusion, not through the elevation difference of the like setting stellarium elevation manually. You're talking about a different thing.
yeah, okay, I got you.
No worries.
Well, I have a couple of questions.
What you got?
Well, so first of all, I just wonder, I mean, I hope we all agree. A stellar occlusion, the time that a stellar occlusion happens is when we see it happen. Does anybody disagree with that?
Yep.
Okay, good. That's question one. I also just wanted to thank you for. I would wait until
John, get to it.
next week. I was thinking maybe it would happen this week, but I totally get that. So I'll be interested in hearing your response. So number two, I'm posting right now this thing. I think everybody agrees on everything on this slide. The geometric angle to the peak, to Pike's Peak from Heffron's Place, calculated on a globe Earth, is in excess of 2.5 degrees. It's 231.3. And I think we agree that it gets lifted a little bit by refraction, but we don't have to. We just agree on the geometric angle. I think we agree that the geometric angle on the globe Earth is lower because of the globe drop. I get 217.7. And I think we all agree that Stellarium says that the star was seen at an elevation of 218.8
John,
at the time of the occlusion, right? I mean, is there anything there that we disagree on?
John, your conclusion is my premise.
Kind of got
What, is there
hypnotized
anything
on
there?
that.
This is a simple question, Alan.
Yes.
It's a simple question. Does
Wh-
anybody disagree?
Does
No,
anyone disagree
that's
on
good,
the
right?
cause
All that
of the
sense.
occlusion,
I,
though?
I
That there was
disagree with your
that there's
tone.
that there's a physical intersection that occurs, and we're comparing physical intersections. You're doing a
I'm not
different.
I'm not
I
going to
know.
go there yet. I
I
just want
know.
to I just want to be clear. We all
Yes,
but do we all agree on those three angles? I don't think there's any controversy about any of those angles. Okay, good. And then the last question is simply this, and it's related to the two things that I'm putting in the chat right now. Oops. Sorry. Right. Now putting in the chat. It's recently come to my attention, and you've said it several times now. You're a core claim, I guess the core claim of the celestial theodolite method is that a star descending toward the western horizon will be occluded by a peak on the globe earlier than it will be occluded by a peak on a flat Earth.
Yep.
And I submit that that's preposterous on its face for the reason that I show there. If you're looking at star descending, it's going to be occluded by a tall peak earlier than it's going to be occluded by a shorter peak. And that's it. That's my last question. Can you explain why you think it's going to be occluded earlier on the globe?
Not only that, I'll show you. But to add to your point real quick, just logically think it
Oh,
out.
but please address my
I just said I'll do that, but just logically think this out real quick. Your refraction is delaying the time, and the later time is the time that flat Earth predicts. So you're delaying the time to match the same flat Earth prediction. Now, I'll explain why. Has to do with this theorem right here, actually. This is the chord tangent theorem. Okay, so an observer on a globe is already deviated by half of the central angle, by whatever the curvature is over that central angle. Okay, so in terms of the sky, positions of the stars, they're following the ground curve 1 to 1 because that's how the celestial and terrestrial sphere emerge. They have the same radius. So the star only has to drop if the star is at 233 for the observer here. It only has to drop 13 arc minutes to intersect at 217 for the geometric peak, which only takes 1 minute and 15 seconds. If the star on a flat Earth, isn't dropping to intersect with a peak at that elevation, it has to traverse the entire arc length before it intersects with the peak. That's going to take twice as long. It takes 2 minutes and 29 seconds. And that's the timing difference that we see here on Stellarium. So if you have an arc second, if you have 13 arc minutes, this is how long it would take to traverse that. If you have 27 arc minutes, that's the full arc length. It takes 2 minutes and 29 arc seconds to establish that, or to traverse that, or drop angularly for that observer. So what happens here is per central angle theorem and inscribed angle theorem and chord tangent theorem, we have leads us to this scenario here. So the globe has an intersection at 1842.04. So if we go into Stellarium observer location and go to where was that? Is this one? Is it this one right here? Yeah. Go to this time, we see that the star is geometrically aligned with the peak for the observer at that time. That's why they predict in earlier time the star, like the ground already did half of the work essentially, because you only perceive half of the central angle. So that applies to the sky as well, and that's why it lines up at an earlier time. And so if the Earth is flat, it has to go the full central angle, which takes a longer time, essentially twice as long.
And the net result of all that is that you claim that if you are sitting there watching a star descend toward the western horizon, you will see it occluded by a mountain peak, a short mountain peak, before it would have been occluded if that mountain peak were taller. That's your core claim.
I just showed it geometrically and showed it in Stellarium. That if the geometry of Earth
Okay,
were
thank
true
you.
1 to 1, that's exactly how it would line up.
I
If
rest
there,
my
if
case.
if
John,
if
you're
there's
not
hold on,
considering
if there's
the
no
sky.
elevation difference of the arc length, then the Earth is flat. So changing the timing difference to the time it takes for the star to traverse the full arc length is what this 13 arc minutes adds back to it. So 13 arc minutes as a timing correction adds 1 minute and 13 seconds back. So it's allowing you to say, hey, you could actually traverse the whole 27 arc minute arc length to get that later occlusion timing. So if you don't consider the earth and sky following curvature 1-to-1, then you're conceptualizing a different model. But this is provable by central angle theorem, chord tangent theorem, and by simply going into stellarium at the observer location, looking at when the star's true position intersects with the same angle as the peak would. Obviously, the timing difference is there. How you optically perceive it is the geometric difference between flat Earth and globe. These timing differences would match what the globe predicts, not add the drop over distance as a time factor back to the time of occlusion. That's crazy.
As I say, I submit my case to the court. Alan's contention is that a star descending toward the horizon will be occluded later by a short mountain than it will by a tall mountain.
And my contention was only met with rhetoric. You didn't actually
Obviously, it's not
geometrically
the
show
case.
why it would be different. You didn't go into stellarium and show why it would be different. When we add 27 arc minutes back to
Because it's simpler.
so 1
It's
second,
simpler
guy.
than that, guy.
Hold on, guy. You're not going to speak over me. So we have the true position at observer location, 2 degrees, 6
That's
arc
so
minutes.
rude.
If we add, what is this speaking over thing? We're not doing that here. So if you add 27 arc minutes to this 2 degrees and 6 arc minutes, you get 233. That's adding the arc length back. That's going to the peak and checking the geometric alignment for the true position at the peak. That's all we're doing. So by you saying that that's ridiculous, but wanting to use a timing correction to match my rise over run to that same arc length is crazy. Now, all you did was simply restate your position in the form of making it seem like my position was retarded, but you didn't show any corrections. You didn't show why it's wrong. You don't have any theorems to back up what you're saying. So again, the globe is just rhetoric and apparent angles.
I have a question.
What's up?
So, you're using this rise over run or whatever to get these angles, but my question is, if you were to take using the trigonometry to get the altitude of Polaris from 2 different latitudes, unfortunately, on the flat Earth, you would get 2 different heights of the star simultaneously because the whole thing breaks down. So I'm just curious why it worked, why you're saying your formula works, but it really doesn't work.
Well, it works just fine, and having the stars converge to a central point just moves them to infinity. Using a conceptual model to find your location on the ground is like two separate things. So having them converge and derive the same elevation isn't necessary. That's not how we would use our conceptual model. The globe is based off of taking what a single observer sees and comparing it to what a single observer would see at the center of Earth. So that's the exact same scenario. That's the exact same ratio that moves the stars at that linear rate for the globe to give the calculated position for a GP defined by the apparent position that you see. So,
I don't think you understood what I was saying.
I understood
Maybe
it.
you were confused. So, okay, so then what? It doesn't work,
It's a
right?
conception. It's a
How could
conceptual.
Polaris be two different?
So our position isn't that we need to physically derive equal angles to a star to have a physical location in 3D space. We don't think that that's a real thing. And just using the conceptual
But that's
model,
math.
1 second, it is math, but just using
Math
the
is
conception, using the conceptual model for navigation doesn't require that convergence for angles per multiple observers. That's a supplemental thing for cosmological purposes. It doesn't serve any purpose. That one guy, if you watch that debate we had, or that I had, Astronomy Live said that he computed nutation, aberration, all these different factors, and ended up deriving the exact same thing that I did without doing any of that. And all these formulas that also do the same thing without doing any of that. So none of those factors actually determine your position on the ground in a way that's meaningful. So just using the model
Hey,
as
Alan?
is for a single observer is all that's relevant. What's up?
I think Stellarium calculates all those in calculating the geometric angle, and he did it himself rather than relying on Stellarium. But it's done in Stellarium,
Yeah.
so you did do it, just you didn't know it, I think.
Well, you see my boys Settlement and GG Bennett refraction right here. These two lads are just using a purely empirically derived formula where you input an angle and they derive the exact same thing. So even though what you're saying is true and I don't disagree with it, it's probably true and I don't disagree with it. Um, these value what just happened here? Shane, are you pressing buttons or something? Anyway, these derive the exact same thing.
Yeah, my bad.
So there's
I was
no meaningful difference in that. And the reason, like heads up, when I go through it and get the time to go through it, like what do you think the odds are that the air density model used by GG Bennett and the boys is going to be the same for the ray tracing?
It shows that they got it really good. They came up with an extremely effective polynomial
Yeah,
that does, in fact, match standard
yeah.
conditions.
And the input and output of those is the globe to make concentric rings going outwards and all that. So it's very circular in that nature, and it's designed such that you can put real world data into it and get these exact results that you would need. So it doesn't. It's not. These aren't the droids you're looking for or whatever.
So, are you aware that Astronomy Live's refraction calculations were based strictly on empirical physics of the speed of light in air at different densities?
Are you aware? I
With
am.
no
Get the same
assumption.
results. How neat.
I am. And are you aware
Okay, good.
that these formulas are derived from just curve fitting observation to what it has to be, and they produce the same value because they're driven by, I'm gonna say, air density. So it's cool that he calculated
You could.
all
Are you
these.
asking me?
I didn't cut out. I said he calculated all of
You
that
did
and
cut
got
out.
this and got the same
Yeah,
answer as the
cut out.
formula. Okay, okay, fine. I apologize. So he may have calculated all of that, but he got the same result that you got that can be gotten from empirically curve fitting by assuming air density to drive the model. So just think about that for a second. You can just put in any angle and this just cranks it out. There's a reason.
That's pretty good. That's pretty good globe evidence, right there.
Yeah, these two are based on curve fitting, Jesse. This is not what you would call good globe
Well,
evidence. Having it based off of a same model where you can,
astronomy.
dude. Okay, Jesse, these two are dependent on just angle. These two are dependent on all these other factors and blah 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 that make it up. Okay, it's a curve fit. This isn't globe evidence. They're driven by the same air density to derive what the angular correction should be per the angle. That's why you can calculate the long form of it and get the same as the short form because it's just curve fitted from the same models.
But Astronomy Live's was not
But the air
curve
models.
fitted,
You're,
right?
Yes, which is the driving factor. Like I
What
said,
was it?
you can change the temperatures of these by like 20-30 degrees and it barely changes it. What was the air density of what
So,
now?
so Astronomy Live said that he calculated it without curve fitting. So are you saying that that's not true? Can you show me the curve fitting in his calculation?
I'm saying I will have to go through it, and the air density section of it is probably going to match the models that they use for this exact same thing for this exact reason. This is why it would match. This is how you could take real world data, calculate it out, get the same proportional refractivity per air density for that angle versus just raw curve fitting it based off of watching circumpolar stars. It's tied to another figure. I'm going to go through
But
it.
I'm telling you, there's no curve fitting.
Listen, just using that amount of air
Okay, super.
density to give the amount of proportional refractivity to get it to arc over 200 and then drop 200 for the observer, to get that proportional amount is going to have to assume a certain amount of air density. That's all I'm saying. And I'm going to look at it and it would literally have to be, because the original value for the air density was derived from just observation and saying this is how much refraction there would have to be for it to be off. And then they just curve fit it. That's why. They're not actually testing it or measuring it or anything like that. They have an assumed value. And then when they translate temperature and pressure to it, it all fits within the model based off of the air density. It's the driving factor of all the atmospheric models.
But those are two different things, right?
Nope. They're
there is no
Those are,
curve.
it's two different things to say, like, this is the observed angle. Hold on, it's a different. It's one thing to say, okay, we need this star to be at this angle based on our model of where the star should be, and then just to say, okay, we'll just adjust it by that much. That's one thing. It's different though to say this is what we observe in the atmosphere. This is what we expect for a path of light given a standard atmosphere.
Yeah, that's
right?
exactly.
You get that,
no,
and you guys have said for
yeah, and
a long time that they did the first. They just said, "Oh, this is the amount we need made up," and then they just put that.
You
amount
in there telling Mama on me? Is that what you doing?
Kid's talking to his dogs. Sorry
Dude,
for that.
I did that once for like I was on a call, and like sometimes Discord will unmute you if you're on a call, and then I like said something to my dude. It was super embarrassing.
Yeah,
but
but no,
he sounded way cooler than I did.
So what I'm saying though is that there's one
It was perfect timing.
There's one specific figure though that drives that, like the importance of it, because the refractivity and air density have to be proportional. Otherwise, you're not going to get a concentric, stratified circles or whatever that they need. So, with that assumption, that's what drives everything. So when they go out and they measure, this temperature, this pressure, it's going to fit in to that model per the air density, and that's how it's going to be distributed. That's why it's the important factor of it. So taking the curve fit and then having it match the derived values that are probably using the same air density value is, it's not proof of the model, it's reifying it. So, and like I said, we're kind of just
I'm pretty content to hear that they didn't just add, because I've heard you guys say that it was the former, that they just put in a number based on what they needed it to be, that it wasn't based on actual curve math for refraction.
Yeah, well, we can do a follow-up
for just like
on all
15
that.
seconds on astronomy.
Yeah, you can
No,
only
it's just
speak,
real quick.
you can
I
only
just wanted
speak
to.
for you only get 8 seconds, Jesse. I'm just kidding. You can get a cool 15, bro. Go ahead.
Oh, thank you,
You really
thank you,
look through
sir.
your data though, or are
So,
you just gonna blind try from the hip again?
so basically, like we understand. Let's say you had two horses running side by
I
side,
figured.
5 feet apart, and one is taking longer steps, but they're both taking the same number of steps and at the same rate. This team of horses will progress in a curved path. Geometrically, if we know how much longer the longer stepping horse, how much farther it's gone, they both go the same time, and they both end side by side just like they started. And to do that, they have to
Running out
curve.
of
Their
time,
path has
Jesse.
to curve. Oh, almost there. Can I have another 8? So that's how.
Yes, please,
That's
yes.
that's how Astronomy Live calculated it. His formula has no up or down in the calculation of the curving. It's just at this elevation, we have the known density. 1 meter above that, we have a different known density. And for a short section, he knows how much the light curves in that section. And then his script does that for every section along the path. It's real cool. It doesn't assume a globe.
Fantastic. And to get that amount of refractivity, you have to have a certain amount of air density. So how fast the horse races is dependent on that input. I rest my case, Your Honor, or whatever. Horse race, however you end a horse race.
And then he had, it was
Yo,
thousands of horse
yo,
races because he had
yo,
balloon data
yo,
going
real
all the way up.
real quick. How many horse races geometrically substantiate the globe? Or was it just apparent ones assuming it after the fact?
Everything.
Gotcha. So every time. All right. So are there any other questions, comments, or concerns? See, next week, like I said, we'll start off with Ruhif because he was first, and then we can get to John's Prezi if it doesn't run too long. If not, we'll do that the following week.
Is
Yeah,
everyone
Yeah, I
here
had
of
a
the
follow up.
opinion that
I
you
had a
can
follow
debunk?
up on my thing that I sent you guys 6 weeks ago. That you
Oh,
guys haven't responded to yet.
The
yeah.
unrelated thing about angles to the who cares?
Yeah, if you do an unrelated thing and that's not analogous to what we're doing, then hats off. And if you don't hear a response from it, that's you can file a complaint with our human resources.
I mean, it was from your guys' presentation.
I know.
I'm the
Go
human
back and
resource.
clip
Now,
it. I
I
can
know.
go back and clip it. I could
Yeah,
find it.
I mean, the fact that you guys haven't responded to my mixtape I sent you, I get, but like Pinky actually sent you something that you like was on
I mean, it's literally on. It's on your Obsidian
Well,
database. I like replied to the actual stuff you guys had published there.
I know.
I have a
and you-
question for the Globers.
Go ahead.
no,
No,
you
hold
didn't,
on.
though.
Shane,
Hold
Shane.
on.
You put
Hang on. Go ahead, Shane.
you put nonsense there. You put strawman arguments. Mostly it's 60% memes. You ended with a declaration that we actually don't trust Stellarium when we use it for everything. You did an analogy. You did a comparison of sun angles independent using just Stellarium to get distances and heights to the sun. Completely unrelated to what we're showing. No geometric intersection comparison. No mutual exclusive model comparing geometric angles. We don't address it because it's silly. If you put an actual refutation together, absent nonsense memes, and then clamor for attention about it for 8 weeks, we'll definitely address it. But if we don't address it, it's because you're not asking any questions, bro.
I can tell you didn't read it. I can
8
tell you didn't read
memes
it.
for 8 weeks.
That's my response to what you just said.
I went all the way through it. You said we don't trust Stellarium.
You
right?
just looked at. I think you just looked
Is
at.
that not in there?
I did
No,
put
no, that's
memes in
the
there. I think you
third-
just looked at the memes and
2/3 of the
that's
way
it.
down. And then you put your whole analysis is based on a tangential thing that Brian did about eclipses. And whatever you want to address eclipses, that really isn't the celestial theodolite topic. We keep trying to say that to you, and you're like, "Ha! No one addresses my thing about eclipses." And Brian is
Well, no,
about
you
eclipses, and
presented it
Brian
as
has
part
no
of
interest
celestial
in
theodolite.
replying to you. Sure, but it has nothing to do
Do you
with
want me to find
geometric
the?
intersection.
Do you remember doing it? Because it was
analysis.
you.
I read the whole thing that you put together, and there was no actual question for us to answer. So if you want to articulate a single answer right now that we can answer for you, that would be great.
Okay, I have 3 of them I don't care about. The main one is, so we're having this conversation about refraction, right? Now the thing about eclipses are occlusions. We know right when they happen. We know when they happen because we can stand in the shadow and we have thousands of data points for it. I thought the idea that you guys brought it up was interesting because we have we don't have to go out and measure mountain peaks. We have actual recorded data. So the question is, why not use those? Why not use those data points? Like, you have everything you need to do celestial theodolite.
Why don't we use
Wait.
data points of known points in a shadow for eclipse comparison? Is that your question? Was that on your webpage?
It's an
Or is that
equivalent.
an ad lib for right now?
Yeah, that was the whole first half of it. was
Okay.
that.
Okay. All right. So you want to say why don't we use points on a map to represent eclipse shadows and then use that because
No,
that's
that's
retarded.
not-
That's why we don't do that.
No.
That's the answer.
You can-
Next.
that's a straw man.
It'll destroy them. It'll destroy them. That's why they can't use it.
It's the worst straw
They'll
man,
be
dude.
destroyed. They'll be destroyed if they
Wait,
use
wait,
it.
Like what are you even talking about, dude?
Wait, for this ether cosmology, as the show has been going, does the flat Earth model, whatever, on the side, is it getting better predictions than the Glober variant? On average, obviously, I know there's here and there's, but on average, is the flat Earth every time? Hey, well, you know what they say: don't hate the player, hate the game. This is a call for the Globers. Come up with a better representation, more predictable of the globe model than what is being represented in this show right now.
If the globe lads can't geometrically,
That's part of what I'm bringing up.
If the globes can't geometrically
Eclipses match the
substantiate
globe so much better.
Okay, 1 second, dog. Eclipses
Can I-
match the globe so much
I do
better
wanna
when you
do
don't
this.
use the same inputs and do a different thing than what Brian did. So, real quick though, if the globe can't substantiate any geometric test to prove curvature, right? And the answer is, oh, it just refracted up to John.
Can everything.
You're gonna make me meet you guys so I can get through the outro here. I got you, bro. No problem. Okay. So if the globe can't substantiate any physicality through the celestial and terrestrial sphere measurements, then there isn't any. If the answer is, oh, we just added back the drop over distance, that just recovers the flat earth angle. It's a literal geometric theorem. So you're not globe lads, you're apparent globe lads. So I would recommend getting together and trying to substantiate physical geometric globe curve. We've substantiated the flat baseline because the timing differences in occlusion require you to invoke as much refraction as necessary to correct the timing so that it matches flat Earth. Now, I'm going to unmute you guys, let you get your final thoughts off, one at a time though, and then we're going to wrap. So, starting with John. Go ahead, John.
The globe method is simple, and it uses nothing more than the fact that a stellar occlusion happens when you see it happen. If you want to predict the time of a stellar occlusion, calculate the elevation angle of the peak using the globe. Well, you can do it with either, but if you do it using the globe drop, incorporating the globe drop, you will predict an elevation angle. And then all you need to do is ask Stellarium, when will the star be at that angle? So for instance, 39 Aquarii is occluded from Mike Heffron's place every single day of the year. And if you want to know when that's going to happen today, simply ask, when will it be at 2 degrees 19 arc minutes? Because that is the elevation angle of Pikes Peak with globe drop.
All right. Thank you, John. And who was it? Rob, did you have one that you wanted to close on? Go ahead, sir.
No, that's okay.
All right. Thank you. Thank you, sir. All right.
Yeah, I
P,
have a
P,
quick
P.
question.
Oh,
I have a quick
sorry.
question.
Go ahead, Wes. What do you got?
Yeah, Shane. Yeah, Shane, why in your presentation with the Excel spreadsheet was there a tab labeled dickhead?
Oh, there wasn't. It said Dickhead's data.
Okay, why?
Well, that's not really pertinent.
It's
to
just
the
a joke.
shape
Get
of-
over it,
It's
bro.
not, it's not really pertinent to the shape
It's
of the
just a
Earth,
joke.
Wesley. PF
Right.
Finky, did you have anything you wanted to close on your eclipses? I know you kind of got cut off at the end there.
We need to do it. You guys ran away from it again for the 6th week in a row, so maybe next week.
All right, maybe next week indeed. All right, let's see here. I think that's everyone. All right, lads, we will be back next
Oh,
week.
sorry. No, I have a quick question.
All right, go ahead.
Do you actually think you're going to address the eclipses next week?
We already went over it. And then the one difference that I kind of agreed with when I was looking at his thing or whatever was the triangle that he drew, and he said that it wouldn't work out or whatever. But Brian used the moon at the 0 elevation, so it would force a right angle triangle. So even the contention that I kind of agreed on at the time is like a non-factor. And again, accomplishing a different goal, like we already kind of went over this, but doing a different goal isn't what Brian did. So it's not analogous and not really.
I mean, I was just asking
It's
if you're
probably
going to
should
talk about it
represent
next week, but
I mean, we've already talked about it, but
Tomorrow's
probably not. There's other more pertinent ones. Like Ruhit's response was way better, and then John's Prezi was haven't watched it yet, but I heard that he talked about some refraction stuff, so we can talk about that. So there's more pressing issues where they're actually talking about mountains and geometric alignments. So those will be, the important ones, I guess.
They're definitely less scary for you guys.
Super less scary.
There's an
Like the
eclipse
eclipse stuff
tomorrow night.
absolutely destroys your case. That's why
course
you
it
guys
does.
won't look at it.
All right.
So
Eclipse
scared.
tomorrow. The
I
eclipse
know,
tomorrow.
All right. Okay, next week.
All right, lads and ladettes, we're wrapping up for the night. See you guys on the next one. Let's see, what do we got here? Got the boys in the chat. We got Shalom, our boy EJ, Packaverse, Pack of Mac Ivers, my boy, Jeff, Flat Bob, Bogan, the classics, dude, all the lads, my boy 101 Mad Mac. You think I don't remember you from the beginning, Mad Mac, when we were reading Crothers together? All right. We'll see you guys tomorrow night for